Hello once again, class, and welcome to another mock lecture. Today, we're going to be talking about the second part of my vectors lecture, and this one is going to be quite long. We're going to be talking about vector subtraction, scalar multiplication, and then finally the dot product. So go ahead and grab yourself a nice cool beverage, sit back, relax, and let me teach you about the last part of vectors here. So we've already done vector addition. We know that if you have two different vectors with position vectors a1, a2, and b1, b2 respectively, then the addition between the two vectors, the sum of the vectors, is a1 plus b1 as the horizontal component and a2 plus b2 as the vertical component, outlined here by the parallelogram rule. But before we tackle subtraction, we have to talk about scalars. A scalar can basically be thought about as a scale factor. So think about like magnifying or reducing the length of a vector. I like to think about it as zooming in or zooming out on the vector itself. That's basically what a scalar is doing. If you think about vector graphics, for example, right? Normally, when you download an image, it's a PNG or a JPEG or something like that. It's what's called a bitmap projection, which has basically put specific colors on each pixel of the picture itself. So if you zoom in, right, so let's say we're going to zoom into this block here. If you zoom into a bitmap projection image, you actually are enlarging the pixels. You're enlarging the squares of color that you see. So if you keep going, you're going to start seeing the individual squares. The image gets kind of blurry. Each pixel basically is getting magnified. But say you're looking at a vector image, right, where now it's not constructed in such a way where each pixel is being colored. The actual image is a vector. Each of the lines that you see is an actual vector that has a specific color and direction and position and all that sort of stuff. So when you zoom into it, you're preserving the smoothness, the crispness of the image, because all you're doing is you're making the vectors in the particular image bigger. This is a vector scale, so each magnitude is multiplied by some specific scale factor, and I just tried to draw in here some visual examples of like what the vectors look like. That's not at all what they look like, but I'm hoping that this does a good enough job at explaining what scalars are doing, which is magnifying the magnitude by a specific scale, okay? So, same thing can be done with just normal vectors, right? Multiplying a vector v by a scalar k results in a vector, right? You just get a magnified or reduced vector, depending on whether your k is something that's greater than 1, in which case you'd be blowing it up, making it bigger, or if it's less than 1 but still positive, then you're shrinking it, right? The vector's getting smaller, you're zooming out in a case like that. So a couple of facts here, I think there's 3. Vector v and k times vector v have the same direction angle. So scalars rather do not change the direction of your vector. They only change your magnitude. But this is only true if k is bigger than 0. Because if k is negative, then k times the vector actually would have an opposite direction angle because you're flipping it around. So do keep that in mind. You can multiply by a negative scalar, and what you're doing is you're changing the direction angle by 180 degrees. The magnitude, of course, is still positive, right? You can't really have a negative magnitude. Each thing has its own length. Each vector has a specific length. Magnitudes can, of course, oppose each other. And as we'll see later, two magnitudes can kind of counteract each other. And we could end up with some negative value when we're looking at some sort of combination of magnitudes. But for right now, I think it's safe to say that magnitudes are all positive. So all we've done by multiplying by a negative scalar is flipped this thing around. And finally, the magnitude of k times vector v is the magnitude, or the absolute value of k. And this is kind of just what I was exactly just saying, actually. It's the absolute value of k times the magnitude of v, so you're going to get some positive value, whether it's flipped around or not. So the magnitude is going to be positive, and in fact, you can calculate it with this. Now, by the way, how do I know this? How do I know that you can calculate it with k times the magnitude of v? Like, you shouldn't just believe me. So let's go ahead and let's examine this, right? Here's a vector v. It's got position vector v1, v2. So you can see its horizontal, vertical components on there. This is the magnitude formula. The square root of v1 squared plus v2 squared. Let's say that we now multiply the vector by k. Now, I'm not going to go ahead and assume that this is k times the magnitude of v, right? I'm trying to prove that. I'm trying to prove to you guys that this is the case. But I do know that if you multiply the vector, if you blow up the vector, right, you've blown it up in a linear sense. So the horizontal and vertical components also get multiplied by this k value. So now this is k v2 for the vertical component and kv1 for its horizontal component. Now, if I want to calculate the magnitude of, let's call it w, right? This is the vector w. Well, here's the formula for its magnitude, right? It's the square root of the sum of its squares of its components. So it's this thing. And then I went ahead and I used the exponent property that when you square a product, you're squaring both parts of the product. Okay, I factored out a k squared, and then I used a square root property, right? I'm breaking up the square root here because we have a multiplication underneath the radical. Well, the square root of k squared, that's just k. And then we're left with the square root of v1 squared plus v2 squared, and those are the horizontal and vertical components for the vector v. So this is really just k times the magnitude of vector v. So the way scalar multiplication works is if you have a vector, right, its position vectors v1, v2, and k is some real number, then the scalar multiple k times vector v is given by k times vector v is equal to k times the position vector, which is equal to component-wise multiplication. You're just multiplying the vector by both of its components by this scalar k. So here's a super quick example, right? Let's say that we know vector v has position vector 3, 4. Let's find 2 times vector v and negative 3 times vector v. I actually didn't do this, but I probably should have found the direction angle for each of them. This video is going to be long enough as it is, so just you should find the direction angle for both of these things when you're done. You'll find that 2 times vector v has the same direction angle, and negative 3 times vector v has an opposite direction angle. Anyway, here's vector v. Also, I knew the magnitude was 5 because that's a Pythagorean triple, 3, 4, 5 triangle. So that I know the magnitude of v is 5. But okay, 2 times vector v, that is going to be 6, 8. The position vector 6, 8, because I'm just multiplying these things by 2, right? Times by 2 there to get that stuff. And the magnitude ends up being 10, okay? Find negative 3 times vector v. Okay, well, negative 3 times vector v, that's negative 3 times the components of vector v. So negative 3 times 3 is negative 9. Negative 3 times 4 is negative 12. So we have position vector negative 9 and negative 12. I think you can, it's at least visually clear that this one has same direction angle as vector v. This one has opposite direction angle as vector v, insofar as they're going in opposite directions. But the magnitude for that one ends up being 15. And again, you should check that with the Pythagorean theorem, but you're going to find the magnitudes are just also multiplied by k. Now, all this stuff is linear growth. Okay, now, the whole reason we went through scalar multiplication is so that it can help us define vector subtraction. Because here's the thing. We know vector addition, right? We know how to do that, and now we know how to multiply by negative numbers. And ask yourself this. What is subtraction other than the addition of a negative? So we're going to go ahead here and let A be the vector A1, A2. B is B1, B2. Those are the position vectors. And I want to define A minus B. So the first thing that we're going to do is find negative B. What is negative b? What's the negative vector for b? Just multiply it by negative 1, right? Because, again, what is subtraction other than the addition of a negative, right? That's all I've done here. I've said a minus b, that's the same thing as a plus negative b. So I'm multiplying vector b by negative 1, which means I'm multiplying its horizontal and vertical components by negative 1, so I get negative b1 and negative b2. And then we're adding, and we know how to add, right? We know how to add vectors via the parallelogram rule. So then we just get a1 minus b1 and a2 minus b2, which stands to reason, right? I mean, if addition is component-wise addition, then vector subtraction also should be component-wise subtraction, and that's exactly what it is. You're just subtracting the 2 horizontal components from one another, and then you're subtracting the 2 vertical components from one another, and that's it. They do have to come in the same order, right? So the vector that comes before the negative sign, right, that's the horizontal and vertical components are coming first. Important to remember, subtraction is not commutative like addition is. If I was to do b minus a, then actually we'd have to find the vector negative a and then, use the parallelogram rule, and that would be a very different vector. Anyway, if a is a1 and a2 and b is b1, b2, the formula for vector subtraction is component-wise subtraction on its components. So here's another super quick example. Let's say p is the vector 3, 0, q is the vector negative 10, 11. let's go ahead and find 2 times vector p minus vector q first, and then we're going to go ahead and find 3 times vector q minus 10 times vector p. So I threw in some scalar multiplication stuff in to make it a little bit more interesting. 2 times vector p, that's the position vector 6, 0, right? This gets multiplied by 2, this gets multiplied by 2, so we get 6, 0. We're subtracting away vector q, and I went ahead and just used this just right off the bat. So that was 6 minus negative 10 for its horizontal component, which is going to be 6 plus 10, that's 16. The other one's going to be 0 minus 11, that is negative 11. So the position vector for 2 vector p minus vector q is 16 and then negative 11. Oh, and by the way, this is what it looks like. That's the resultant vector there. Now for the next one, I did something just a little bit different. 3 times vector q minus 10 times vector p. Well, 3 times vector q, that's negative 30 times 33, right? These things get multiplied by 3. And then vector p times 10, right? That's 30 and 0. And what I did here is I actually changed this into the addition of the negative components for 10 times vector p. And I did that so that it visually makes a little bit more sense. Here is actually negative 10 times vector p. And then I'm going to go ahead and I'm going to find the resultant vector by using the parallelogram rule here. But anyway, let's go ahead and do the component-wise addition now, right? Since I went ahead and I distributed the minus 1. So we have negative 30 plus negative 30, that's going to be negative 60. And then 33 plus 0, that of course just is 33. And so this is the resultant vector. Again, via the parallelogram rule, right? There's negative 10 vector p up there. So the diagonal between them, since we're adding now, that is going to be the resultant vector, negative 60, 33. Okay, so let's move on to something pretty cool. There's actually a second way to deal with vectors, right? If you're like, oh man, all this component-wise stuff is really confusing me, there's a different way to approach this stuff. And actually, it's very algebraic. If you're an algebra type of person, which is me, I love algebra, then you're really going to like this method. We're going to go ahead and let I be the unit vector 1, 0. So it basically represents this vector. Right? Here's the xy axis. That is a terrible x-axis. But this vector is just on the x-axis, and here is the point 1, 0. Right? That's I. Of course, it's a vector, so it's got a direction and all that stuff. And a magnitude, and its magnitude is 1. J is this vector. Right? This is the point 1, 0. But again, it's a vector, so its magnitude is 1. It's got a direction angle of 90 degrees in that case. So I and j are the horizontal unit vector and the vertical unit vector, respectively. And so that's what I put here. I is 1, 0, j is 0, 1 as vectors. So if you don't like, right, this notation with the angled brackets and such, then you can write it algebraically as a1 times I plus a2 times j, which will make addition of vectors and subtraction of vectors and dot product and all the other stuff that we do actually very algebraic, instead of maybe foreign is the right word, because this can take a little bit getting used to, but this notation kind of saves us from looking at kind of weirder entities like a position vector. By the way, you shouldn't believe me, right? I mean, I'm saying that these two things are equal, but really, how do you know that? Right? Well, I'm going to show you. I'm going to prove it to you. Right? Quick proof outline with no justifications. Ready, go. First, we're going to start with the right-hand side in this particular case. We have a1i plus a2j. That is equal to a1 times the position vector 1, 0 plus a2 times the position vector 0, 1. Via some scalar multiplication stuff, we know that that is then just going to be a1, 0 plus 0, a2. We already know how to do vector addition, so we get a1 and a2, so we know that they're equal because a1 plus 0 is just a1 and 0 plus a2, that's just a2. Done. It's true. I would never lie to you. Well, intentionally anyway. Okay, anyway, so let's just do that exact same example that we just did, but now with this new notation. So vector p and vector q can be rewritten as 3i plus 0j and negative 10i plus 11j respectively. So let's go through these again, right? Starting with a here. This can be thought of as 2 times 3i plus 0j minus negative 10i plus 11j. And at this point, it's just algebra. Just algebra your way through this. This is 6i plus 0j via some distribution. This is going to be positive 10i minus 11j. Adding some like terms together gives us 16i and negative 11j. right? Which is the position vector 16, negative 11. And if you go back 4 minutes or so, I'm totally guessing, then you'll see that we found that same thing for A. Part B, same thing, right? It's all just algebra right at this point. Do the distribution. You have 3 times vector q, that's negative 10i plus 11j, minus 10 times vector p, that's 3i plus 0j. I just did a bunch of distribution, combined some like terms, and you end up getting the exact same position vector that we got just a little bit ago. So let's talk about the dot product, or maybe vector multiplication in general, because there's 2 ways to find a product, as it were. There's the dot product, which is what we're going to do. That's something that actually produces a sort of combined magnitude between 2 vectors. Kind of, not really, because you can actually get a negative value when you do the dot product stuff. So it's not, I wouldn't think about it as just magnitudes, but it's some sort of combined magnitudes. How much do the magnitudes of 2 vectors affect each other based on their direction? Maybe that's a better way to think about it. The cross product, it produces a vector. So instead of just getting a number, which is what the dot product gives you, some real number, you actually get a vector when you do the cross product. Although typically this is used for 3-dimensional vectors, and it's reserved for kind of physics with calculus sort of stuff. So we're not going to get into that here, but we will talk about the dot product. And I think that, and it does produce a real number, and I think that a good starting place to think about what this is it's basically the multiplication between 2 vector magnitudes. It's not exactly that, though. And so we're going to use this to kind of extend our understanding of what the dot product is. But again, I think this is a great starting point, a product between 2 magnitudes. But it's only a product between 2 magnitudes if the vectors are going in the exact same direction. Okay, so if it was something like this, right, vector v, vector w, which appear to have 0 degrees as its direction angle, as both their direction angles, then vector v dot vector w is indeed the magnitude of v times the magnitude of w. But that does not always happen. In fact, it's pretty rare, right, that we're talking about 2 forces that are going in the exact same direction. So more than likely, this is going to be our case. Vector v and vector w don't have the same direction angle. Now, I know that I've drawn it here such that it looks like the direction angle for v is 0 degrees. And I just did that for simplicity. Because here's the thing, right? And I know the first thing that I should mention is I do know, as you probably do, vectors have direction and magnitude. We can't just willy-nilly change the direction of a vector. For dot products, it actually doesn't really matter, right? We're talking about relative direction angles, right? What is the direction angle of vector w relative to vector v? That's what matters, right? Kind of this angle is the thing that matters when we're talking about the dot product. So even though vector v could look something like this and vector w something like this, we can rotate it down such that, because this angle doesn't move, right? This angle's the same. Whether we rotate this thing down so that vector v is coincident with the x-axis or not, the dot product, which doesn't give you a vector as its product, it gives you a scalar, it gives you some kind of real number, is not affected. So even though I know vectors have a direction angle, we cannot just change them willy-nilly. In a dot product sense, we are kind of allowed to do that because we're preserving the angle that is between both of these vectors. So vector v drawn as the x-axis effectively for simplicity here. And what we're asking, right, this is really what the dot product gets at, is how much does vector w influence vector v's direction? We can answer that whether or not this thing is rotated so that such that one of its vectors is on the x-axis or not. It doesn't really matter. It's all about the relative position that we're looking at these 2 vectors in. So now, why am I drawing it like this? What's the whole point of drawing it like this? Well, imagine that there's a light bulb that's placed directly above the terminal point for vector w. If there's a light bulb here, and let's say that vector w and vector b and the light bulb are all in the same plane, then the light bulb is going to shine on vector w and it is going to create some kind of a shadow that is projected onto vector v. That shadow is effectively how much of the magnitude of vector w is affecting vector v. So that's what I put here. This shadow is the projection of vector w onto vector v, and a typical dot product is the product of the vector's magnitude and the magnitude of this projection of vector w onto vector v. So in this example, the dot product is the magnitude of vector v times the magnitude of this shadow, which is the projection of vector W onto vector V. Right? So instead of just saying, oh, it's the magnitude of vector V times the magnitude of vector W, which again is only true if your direction angles are the same, right? So if the vectors are going in the same position, you simply just multiply their magnitudes. That is very, very rarely the case. So what you have to do is kind of do this light bulb projection thing. So you're projecting a shadow onto vector V, which, by the way, happens to be the horizontal component for vector W. Right? Because you might be asking, how the heck do we figure out what the magnitude of the shadow of vector W projected on the vector V is? That's an excellent question. But again, notice that if we give vector W a position vector W1, W2, then it's actually just W1. W1 is the shadow here, right? So we have theta, a horizontal component, and a hypotenuse of a right triangle. So we can set up a trig ratio. We can say cosine of theta is equal to adjacent over hypotenuse. So we get W1, the horizontal component, over the magnitude of W, right? That's what this length is, the magnitude of W. So then we know that W1, right, if you want to solve for the horizontal component, you would just multiply both sides by the magnitude of vector W. So this is how we find it, right? That straight up replaces this, and so this is the dot product. Vector V dot vector W is equal to the magnitude of V times the magnitude of W times the cosine of theta, which is actually just the horizontal component, right, of vector W. Now I know you're thinking, you're like, okay, well that's fantastic, right? But oftentimes we aren't really given the angle between the vectors. It'd be really nice if we could have a formula for the dot product that just uses the components of the vectors themselves. And that's a very good observation. Let's do that. Let's figure out what the dot product is in terms of, just using the horizontal and vertical components of each of our vectors. To do that, we're going to need to start by finding negative W. So I'm going to go ahead and create a right triangle here. Not a right triangle. I'm going to create a triangle for which I'm actually going to use the law of cosines, of all things, to figure out what the formula is for the dot product in terms of just utilizing these components here. So again, starting off by finding negative W, I'm going to add the two vectors, V and negative W, which is actually the subtraction of W from V, using the parallelogram rule here. So we've got a triangle. We know all of its lengths, and the angle theta here is the same angle as this one because it's a line that's intersecting two parallel lines. So they're kind of alternate interior angles that we're looking at here. But we know all the sides of the triangle. It's a side-side-side situation, so we know law of cosines is going to come into play. This length is the magnitude of V. This length is the magnitude of W. This length is the magnitude of V minus W. So from the law of cosines, we get this thing. I'm not going to read that whole thing, but there it is, right? It's from the law of cosines. Then what I did is I actually just replaced this with V dot W, right? It's vector V dot W. And we need to find that. I want to isolate this thing because if I can figure out what this is, I'll have something only in terms of a bunch of components for V dot W. So this is the magnitude formula. This looks like an absolute mess, mostly because it is, but we're going to simplify the heck out of this thing here in just a second. Again, I'm not going to go through every single line here, reading it all out, but there it is for you on screen. I'm just using the magnitude formula to find this stuff. Notice, though, that all of these square roots are being squared, so I'm going to go ahead and get rid of all that stuff. So I got rid of all that stuff, and then I'm also expanding those two things. Again, the square roots went away, but there's still, let me go back a couple slides. There's still that squared hanging out here. That doesn't cancel. The square root is only canceling with this thing. So then I'm expanding this, right, to give me this. Just FOIL method, right, or box method. It happens twice. Happens for this one, happens for this one. Nothing happened over here. Just stayed the same. But notice now that there's a whole bunch of similar terms, exactly the same terms, on opposite sides of the equation, so they cancel. V1 squared, V1 squared, those are gone. V2 squared, V2 squared, right, those are gone. W2 squared, W2 squared, W1 squared, and W1 squared. Where's my W2? Oh, I think that one actually should be W1. So dang it, there is a typo there. So I'm so sorry about that, you guys, but it does cancel. It's W1 because it's the square of this thing here. Okay, so all of those things cancel, and you're just left with negative 2v1w1 minus 2v2w2 is equal to negative 2 times the dot product between v and w. Well, now just divide everything by negative 2, and you're done. Right, that's it. That's the dot product in terms of just components. It's so easy too. It simplifies into something super nice. V1W1 plus V2W2. That's the dot product in terms of its components. Now, by the way, I think it is worth noting, and I'll have us do an example of this really quick here in just a second, but you can actually solve for the angle between the two vectors. Instead of like finding the direction angle of V and then finding the direction angle of W and then trying to finagle your way to figuring out the angle between them, which you can do, that's totally valid, but just using this first dot product formula, you can actually find a really concise formula for theta. You just have to know the dot product already. That's the one downside. You have to know V dot W to figure out what theta is, the angle between them. But that's fine. Let's do an example and I'll show you why. Okay, so example 3. Suppose that vector A is 2i minus 3j and vector B is i plus 5j. Number 1, sketch both these vectors. Number 2, we're going to find the dot products between them. And then number 3, we're going to find the angle that's between them as well. 2i minus 3j has a position vector 2, negative 3. There it is. I plus 5j has position vector 1, 5. There it is. Number 1, complete. Now we're going to find the dot product right between these two things. Now, and first, before we find this, just notice these vectors they're not really going the opposite direction, but they are going kind of opposite, right? They're definitely not helping one another much as far as influence over one vector goes. Okay? Like if you project a shadow, you may not really get much of a shadow that's projected onto vector A if we were to rotate this thing such that A was coincident with this thing, right? Probably, in fact, you wouldn't get a shadow at all if we're going to use that kind of analogy here to think about what's going on. So you're going to have something we're going to get a negative number. That's kind of what I'm getting at here when we calculate this thing. A1B1 plus A2B2 is the dot product, just utilizing its components here. So that's 2 times 1 plus negative 3 times 5, which gives us negative 13 as the dot product. And the negative in my mind just kind of tells me, oh, hey, so it is possible to get a negative value when you do the dot product. It doesn't really make much sense in terms of kind of how we preliminarily set this whole thing up. Like how much does vector B affect vector A? It's a combination of their magnitudes, but magnitudes can't be negative. So the analogy does kind of break down here a little bit. It was mostly just to help kind of set it up. But negative dot products are certainly possible. And here we're getting one, right? We're getting the dot product to be negative 13. So that's done. Find the angle between vector A and vector B. Well, we have a formula, and we actually already know the dot product. So we can go ahead and fill that in. What we don't know, though, is the magnitude of A and the magnitude of B. We can very simply find them by using the formulas for their magnitudes. I got 3.61 as the magnitude of A and 5.1 for the magnitude of B. Plugging those things in gives us the cosine inverse of a negative 0.706. Now, before we move on, I just want to point out that this is going to give us something that's in quadrant 2. Cosine inverse only exists between 0 and 180 degrees, right? 0 and 2 pi. So the fact that we're plugging in something negative, right, means that we're going to be forced to be in quadrant 2 for cosine inverse. But what I want to point out is that it actually doesn't matter. We can actually completely ignore the fact that we're going to be in quadrant 2 for this angle, because this is basically, if we move, we're finding this angle here. Okay, that's what we're doing. If we rotate this entire triangle up so that A is coincident with the x-axis, that also moves B, vector B, this direction, and this angle here is going to be the same as this angle here. So even though we're going to land in quadrant 2, the angle between the vectors is preserved when we're finding this angle. That's why when we set up the whole dot product thing, I wasn't really concerned about making it so that vector V was coincident with the x-axis. So all that to say that we just get 134.92 degrees, and I just plugged it into my calculator to figure that out. So that's done. Next example, which is really example 4. A common dot product application is called work. It's a physics thing. If a constant force F is applied to an object that moves along vector D, then the work W done is given by W is equal to F dot D. Basically, in science, it's a force that forces only do work when an object is moved, basically. So for example, if a person is pushing against a brick wall, the wall's not moving. That's not doing any work, right? And the object has to move for work to be done. So a person that's lifting like a 5-pound weight, right? That's a specific amount of distance, right? That's doing work. Okay, in general, I think it's safe to say that work basically is force times distance. But again, that's only provided because that's what the dot product is as well. But that's only true if the forces have vectors that are in the same direction. Okay, so instead, we're using the dot product thing because very often we're in situations where the forces are acting in different directions, right? So that's where the formulas for the dot product come into play rather than just saying, oh, it's just force times distance. So the example is really here. Find the amount of work required to push a 2,400 pound car up a 6-degree incline. And let's say that specific incline is 700 feet. Maybe it's like a super long driveway or something like that. And the car's stalled. That's why we have to push it. So first we got to figure out what the vectors look like. So I went ahead and I drew the kind of distance vector. It's a 6-degree incline. We're pushing the car for 700 feet. So we know the magnitude is 700. But that doesn't really tell us what the position vector is, right? Even though we know the magnitude is 700 feet, we still need to figure out what the position vector is. And you have to kind of recall back that to find the vertical and horizontal components, you have to use the magnitude times sine and cosine of the angle respectively. Okay, so it looks like this. The position vector, and I just call it the vector D, is 700 cosine 6 degrees and 700 sine 6 degrees, which gives us this as the kind of incline vector that we're working with here. Now, for us to actually push this car, we have to overcome the weight of it. Okay, so we're working against gravity here. So you would think, okay, well, it's 2,400 pounds, right? And gravity's already making it that heavy. We have to overcome that though. So the vector that we're working with is actually a vector that's pointing up. It's got a 90-degree direction angle. We're trying to overcome the force of gravity. So the force vector then is 0 positive 2,400, right? I think it's very easy to say, well, wouldn't it be 0 negative 2,400 since you know, gravity and everything? But no, we're trying to overcome it. So we have to make the force, the vector, be a positive 2,400 for its vertical component. Then we're just going to find the dot product between these two vectors, right? So F dot D is F1D1 plus F2D2. That is 0 times 696.2, which is 0. So this component basically is meaningless, goes away, because we're pushing it in kind of a horizontal-ish direction anyway. So that's the one that really matters. Anyway, so the next one, we're adding that to 2,400 times 73.2, which gives us 175,607.8. And then you might be wondering, what is the unit for work? It's a foot-pound. Okay, so hopefully those two examples were helpful. Hopefully this whole video was helpful. I know it was a little long, so thanks a ton for sticking around. If you guys have any questions, any comments, please drop them in the comments section below. Thanks a ton for watching, and I'll see you in the next one.